The launch of NASA's Voyager probes marked the commencement of an extraordinary journey into the depths of interstellar space, showcasing our ability to explore not only Earth, but also the vast expanse of our solar system and beyond. These remarkable spacecraft, which have been traveling for 45 years, continue to provide scientists with fresh insights about the cosmos. Despite having memory capacity 3 million times smaller than a typical smartphone and processing speeds 38,000 times slower than a 5G internet connection, these incredible probes remain at the forefront of space exploration. But now, in an astonishing twist, the Voyagers have made an unimaginable discovery. What are they up to presently, and what will they encounter next? Let's dive into it. The remarkable journey began on September 5, 1977, when Voyager 1 was launched from Cape Canaveral, Florida, riding atop the Titan III Centaur rocket. Merely 15 days later, on August 20, 1977, Voyager 2 embarked on its own mission, starting a twin odyssey into the cosmos. Initially tasked with exploring the gas giants Jupiter and Saturn, as well as their moons, these intrepid explorers far exceeded their original objectives, embarking on a voyage that would take them to the farthest reaches of our celestial neighborhood. Voyager 1 and Voyager 2 have achieved numerous records during their epic journey. They have outlasted all other spacecraft in history and have ventured further from Earth than any other human-made objects. In fact, they have entered interstellar space, becoming the first human-created objects to do so. Their journey into interstellar space, beyond the influence of the Sun and into uncharted galactic territory, has provided scientists with invaluable data. Even more astonishingly, as pioneering interstellar probes more than 12 billion miles from Earth, they continue to surprise physicists with their findings. The recent and perplexing discovery is one such find that scientists could never have anticipated. We will delve deeper into it shortly. The accomplishments of the Voyager twin probes have been nothing short of spectacular. Their early observations of the moons of Jupiter and Saturn, made over 40 years ago, left researchers astounded and challenged prior assumptions about these distant worlds. These moons, once believed to be as inactive and heavily cratered as our own moon, were revealed to be brimming with geological activity. Voyager 2, in particular, reached significant milestones during its journey. It became the first spacecraft to pass by Uranus in 1986, and just 3 years later, it conducted a flyby of Neptune. To this day, it remains the sole spacecraft to have ventured on such a path. As these spacecraft continue their extraordinary voyage, NASA has implemented a series of measures to extend their operational lifespans. Over the past 3 years, non-essential components and heaters have been deactivated to conserve energy, enabling them to operate well into the next decade, with an estimated mission end date of 2030. For the scientists and engineers who have been part of this extraordinary journey from the very beginning, the culmination of the Voyager missions is a moment of mixed emotions. Their unwavering dedication and hard work have carried the project far beyond their initial expectations. The data returned by the Voyagers has yielded valuable insights, driven countless scientific discoveries, and inspired generations of researchers and space enthusiasts. Voyager 1 and Voyager 2 were not just ordinary spacecraft. They were meticulously designed as stable platforms with a rotation rate more than 15 times slower than the hour hand of a clock. This design minimized visual blurring as the spacecraft captured images and data while hurtling through space. Their impressive imaging capabilities began to astonish scientists and the public even before their encounters with the outer planets. The spacecraft started transmitting images of Jupiter while still several months away from the planet. These early images, revealing the gas giant's swirling clouds and iconic Great Red Spot, captivated audiences at NASA's Jet Propulsion Laboratory. However, the true stage for the Voyager's groundbreaking observations was set by the discovery of active volcanoes on Jupiter's moon. Io, slightly larger than Earth's moon, turned out to be the most volcanically active body in the solar system. The spacecraft's instruments detected peculiar signals from Io, which were confirmed by the vivid images they captured. These images unveiled towering volcanic plumes and a surface marked by the ejection of volcanic material. For instance, Pele, one of Io's most prominent volcanoes, has erupted 30 times higher than Mount Everest, covering an area nearly the size of France. The Voyager spacecraft captured over 33,000 images of Jupiter and its moons, showcasing the planet's beauty and the incredible diversity of moonscapes in the Jovian system. Prior to the recent astonishing discovery, the twin Voyagers have been consistently making remarkable findings since their launch. One of the most surprising revelations was the existence of Jupiter's rings, a faint but intriguing addition to the gas giant's allure. Voyager 2 also unveiled that Europa, one of Jupiter's 53 named moons, possessed an icy shell believed to be over 60 miles thick. These findings challenged prior assumptions about the nature of these distant celestial bodies and spurred further investigations into the potential habitability of icy moons. As the Voyagers bid farewell to Jupiter, they received a gravity assist that propelled them towards Saturn. This crucial boost was necessary for them to escape the sun's gravitational pull and continue their journey deeper into space. Voyager 1's path led it near Saturn's moon Titan, which is enveloped in an orange, hazy atmosphere. The mysteries of this moon piqued the interest of scientists, leading to further studies of its complex chemistry. Voyager 1 then altered its course, heading northward and departing from the plane of the planets, embarking on a voyage beyond the confines of our solar system. Voyager 2, on the other hand, embarked on a remarkable series of voyages that took it to the farthest planets in our solar system. In 1986, it achieved a momentous flyby of Uranus, where it made an astounding discovery of 10 previously unknown moons, adding to Uranus's moon count. 3 years later, Voyager 2 reached Neptune, unveiling the astonishing features of this distant ice giant. During its encounter with Neptune, Voyager 2 recorded wind speeds reaching up to 1,000 miles per hour, marking the highest wind speed ever documented on any planet in our solar system. As the spacecraft passed within 2,980 miles of Neptune's azure, methane-rich atmosphere, it provided unparalleled insights into this remote world. Triton, Neptune's largest moon, emerged as one of the coldest places in the solar system, with surface temperatures plummeting to minus 391 degrees Fahrenheit, minus 235 degrees Celsius. Triton also exhibited unique characteristics, including ice volcanoes ejecting nitrogen gas and icy particles 5 miles into its thin atmosphere. These discoveries expanded our understanding of the diversity and complexity of our initial objective's solar system, even in its outermost regions. One individual who played a pivotal role in extending the missions beyond their initial objectives was the renowned astronomer Carl Sagan. As a member of the Voyager mission's imaging team, he passionately advocated for capturing a final set of images before the cameras on both spacecraft were powered down. These images would serve as a parting gift to humanity, offering a final glimpse of our home planet from the distant reaches of space. Sagan's persistence paid off. On Valentine's Day in 1990, Voyager 1 turned its camera back toward the inner solar system and captured a sequence of 60 images. The most iconic among them, known as the pale blue dot, remains an unforgettable symbol of our place in the cosmos. Taken from a distance of 3.8 billion miles, it stands as the farthest image of our planet ever taken. Earth appears as a minuscule, pale blue speck, barely distinguishable in the vastness of space. The Voyager mission is an astonishing tale of resilience and longevity that reads like a space-age superhero comic. Even after 40 years, they continue to transmit valuable data from the farthest corners of our cosmic neighborhood. Now, let's delve into their antiquated 8-track tape system. Yes, you read that correctly. 8-track tapes were all the rage in the 1970s, and the Voyager probes are still equipped with them. It's a testament to the ingenuity of the mission's designers that these trusty tapes have endured the test of time. But why 8-track tapes, you might wonder? In those early days of space exploration, digital storage as we know it today was still in its infancy. Therefore, a reliable and durable data storage system was needed, and those 8-track tapes fit the bill. They're like the unyielding workhorses of the space age. What's even more incredible is that the data on these tapes isn't just your typical music. It comprises valuable scientific data about the outer planets, moons, and interstellar space. These tapes hold the key to understanding some of the most profound mysteries of the universe. Regarding durability, consider this. The Voyager spacecraft endure extreme temperatures, cosmic radiation, and the vacuum of space. Yet, these aging explorers persist and thrive. It's akin to sending your grandparents on an expedition to Antarctica, and not only do they survive, but they flourish. Now, let's explore the strategies that ensured the success of the Voyager missions. One critical technique employed in the Voyager missions was the use of gravity assist maneuvers, and their role in these legendary interstellar missions was nothing short of brilliant. Imagine two intrepid spacecraft, Voyager 1 and Voyager 2, embarking on their audacious quest to explore the outer reaches of our solar system. To reach these distant destinations and gather invaluable data, they required a boost beyond what their own propulsion systems could provide. This is where gravity assists come into play, and it's somewhat like a celestial dance. Instead of solely relying on their engines, these spacecraft engaged in a cosmic choreography with some of our solar system's heavyweight planets, utilizing the immense gravitational pull of these giants to sling them further on their journey. This ingenious maneuver allowed them to conserve precious fuel and gain the velocity needed to visit multiple destinations on their grand tour. To break it down, a gravity assist, also known as a gravitational slingshot, involves transferring some of a planet's momentum to the spacecraft as it passes by. Visualize Voyager 1 approaching Jupiter, a colossal gas giant with a gravitational pull to match. With precision that only the brightest minds at NASA's Jet Propulsion Laboratory could achieve, Voyager 1 maneuvered past Jupiter at just the right angle and speed. Jupiter's gravity pulled at the spacecraft, accelerating it to a higher velocity, akin to a cosmic boost that provided Voyager 1 with the required momentum. However, this maneuver requires remarkable precision. If Voyager 1 had approached Jupiter at the wrong angle or speed, the slingshot could have led to a cosmic catastrophe, veering the spacecraft off course. The level of precision required is mind-boggling. Yet the scientists and engineers behind this cosmic ballet not only got it right once, but multiple times. These gravity assists propelled Voyager 1 and Voyager 2 on a breathtaking journey through the solar system. Consider Voyager 2, for example. It harnessed the power of gravity assists from Jupiter and Saturn, which served as celestial slingshots to propel it towards Uranus and Neptune. These celestial maneuvers were absolutely essential for the success of the Grand Tour missions. Without these gravitational assists, the Voyager expeditions would have been entirely different. Voyager 1 ventured into interstellar space, and Voyager 2 closely followed suit, all thanks to the precise execution of these gravity assists. The concept behind gravity assists may be simple, but the execution is incredibly complex. Voyager 2's Grand Tour demanded exceptional precision. Missing any of these slingshots could have spelled disaster for the missions. However, the individuals behind these missions were determined and unwavering in their pursuit of knowledge. While the Voyager missions made ingenious use of gravity assist maneuvers to traverse the cosmos, they would have remained mere celestial fantasies without another vital component, the Deep Space Network, DESN. Think of it as the interstellar telephone line that kept us connected with our intrepid Voyager probes as they ventured into uncharted territory. But what exactly is the Deep Space Network? It may not be as glamorous as a spacecraft, but it is just as indispensable. The DSN constitutes a network of enormous radio antennas strategically situated in various parts of the world, including California, Spain, and Australia. These colossal dishes, ranging from 26 meters to a whopping 70 meters in diameter, are like cosmic loudspeakers, enabling us to communicate with spacecraft venturing beyond our planet. Now let's discuss its role in the Voyager missions. The Voyager probes, equipped with cameras, sensors, and instruments, essentially served as our eyes and ears in the vast expanse of space. To interpret the data they transmitted and provide them with new instructions, we required a robust communication system, and that's precisely where the DSN came into play. Imagine this scenario. Voyager 1, en route to the outer fringes of the solar system, transmits a message back to Earth. It's a faint signal traveling at the speed of light, weakening as it traverses the cosmic abyss. By the time it reaches Earth, it's scarcely a whisper. Nevertheless, the DSN's colossal antennas are poised to capture that faint signal. They lock onto Voyager's feeble transmission and amplify it, converting it into data that scientists can analyze. The DSN doesn't merely receive signals, it also transmits commands. You see, missions like Voyager are dynamic. Scientists and engineers need to fine-tune their plans, alter the spacecraft's course, or adjust their instruments. They relay these commands through the DSN, which beams them into space to reach Voyager. It's a two-way conversation between Earth and the farthest human-made objects in the cosmos. One of the remarkable aspects of the DSN is that it operates around the clock, tirelessly listening for those distant signals. It's like having an unwavering eye on the cosmos, ensuring our connection with our spacecraft remains intact, even when they are billions of miles away. The Voyager missions stand as a testament to the power of collaboration and innovation. While the spacecraft embarked on their incredible journeys, the DSN ensured they were never truly isolated. It bridged the gap between our planet and the unknown, enabling us to explore the outer planets and venture into interstellar space. In essence, the Deep Space Network is not merely an assemblage of antennas. It represents our lifeline to the cosmos. It guarantees that the narratives of the Voyager missions persist, even as the spacecraft venture beyond our solar system into the uncharted realms of interstellar space. So, what is the heliopause, and what fascinating discovery did Voyager 2 make there? As the Voyager probes embarked on their interstellar odyssey, one of the pivotal milestones they had to navigate was the heliopause. This is the boundary that separates the influence of our Sun from the vast interstellar space beyond. Initially, the exact location of this boundary was somewhat enigmatic, with varying estimates and theories. Early approximations placed it as close as Jupiter, but subsequent calculations refined our understanding. In 1993, astronomer Bill Gurney's projections positioned the heliopause between 116 and 177 astronomical units, AU. To put this into perspective, 1 AU is approximately 93 million miles, which is the distance between Earth and the Sun. Gurney's projections turned out to be remarkably accurate, as Voyager 1 reached the heliopause about 20 years later and detected the expected rise in plasma density. However, this discovery posed a perplexing question. When Voyager 1 reached the heliopause, it observed an increase in plasma density, but no significant change in the direction of the ambient magnetic field. This was unexpected, as a noticeable shift should have occurred if the spacecraft had transitioned from a region where the magnetic field originated from the Sun to one where it came from other stars. Voyager 2 deepened the mystery when it reached the heliopause at the same distance as its twin, 120 AU from Earth, but also failed to detect any magnetic field changes. Theoretical models predicting the behavior of the heliosphere and its interaction with the interstellar environment faced challenges due to these unexpected observations. The heliosphere was expected to fluctuate in sync with the Sun's 11-year cycle, but this did not align with the data collected by the Voyagers. The solar wind, which ebbs and flows with the Sun's cycle, was at its strongest when Voyager 2 arrived at the heliopause. Nevertheless, the data from the Voyagers have offered valuable insights for refining theoretical models. Scientists now believe that our Sun has transitioned from a hot, ionized zone to a partially ionized section of our galaxy. This transition was likely triggered by nearby supernovae, ancient stars that exploded at the end of their lives, heating the surrounding region while stripping electrons from adjacent atoms. The boundary between these regions can be likened to a shoreline, with turbulent waves and mixed magnetic fields. While the degree of turbulence can vary, the Voyager's observations have revealed small-scale changes near the heliopause, but negligible variations on larger scales. The ageless explorers, Voyager 1 and Voyager 2, continue their solitary journeys through interstellar space, leaving behind the planets and moons they once called home. But what awaits these indefatigable travelers in the future? It's a cosmic enigma, but here are some possibilities to contemplate. These probes are now moving in opposite directions, with Voyager 1 racing toward the constellation Ophiuchus, while Voyager 2 is making its way towards the constellation Cetus. Despite predictions by some scientists that they might encounter a cosmic demise in 2030, they may still endure for millions of years. They might someday encounter other star systems, bearing with them a message from a long-lost Earth. Imagine an extraterrestrial civilization stumbling upon these ancient artifacts of human ingenuity, including the Golden Record, a time capsule of our existence. The mysteries they might unravel are truly boundless. Thanks for watching. Please don't forget to like, comment, and share.